Hello, I'm Yangqing Huang from NCTU Taiwan. I will present you the research about optimal functional split for processing sharing-based comp for mixed eMBB and URLC traffic, which is accepted by GlobalComp 2020. This is the outline. The introduction, system model, and problem formulation are given. Then the algorithm as solution is proposed. Finally, the conclusion and results are given with performance evaluation. 5G has defined several services such as eMBB, URLC, and MMTC. Each has different requirements. eMBB aims at achieving higher data rate, while URLC requires low latency and high reliability. It's challenging to satisfy all requirements at the same time. In the meantime, network virtualization is able to adjust centralization degree by flexibly placing functional sublayers as centralized unit (CU) or distributed unit (DU). More centralized architecture has advantage of implementing coordinated multipoint (COMP) transmission at the expense of stringent latency requirements, while the distributed one requires comparatively low frontal capacity. Here lists some related works of flexible functional split, where functional split is not fixed by hardware infrastructure, but can be adjusted by virtualization. However, the flexible selection of functional split mode, FSM, for each user equipment, UE, based on their individual service requirement is still an open problem at present. Motivated by aforementioned literatures, our contributions are listed as follows. This paper is the first work to investigate optimization problem on choosing a feasible FSM for each UE. Delay outage probability. DOP of UEs with URLC service requirements should be minimized, while mean signal to interference plus noise ratio, SINR constraints should be achieved. We propose a two-step optimal FSM decision algorithm, OFD, and it is guaranteed to achieve a globally optimal solution based on the convexity of a derived DOP function. Here comes the system model part. Since packet size in eMBB service is usually much larger than one in URLC, the requirement of URLC is easily violated in first come first serve (FCFS) server, while processor sharing server is preferable solution since it equally allocates its service rate to all packets currently in server, as shown in Figure 1. We consider flexible functional split network consisting of a single CU, multiple DUs, and UEs, which obey Poisson point process (PPP). The Q model of servers in both CU and DUs is characterized by MG1 processor sharing model. Lambda D is denoted as density of DUs. Lambda S and mu S is the density and packet arrival rate for service S, where S belongs to E and U for eMBB and URLC service. This is the illustration of system model. The considered flexible functional split network can support two FSMs, named centralized control mode (CM) and distributed control mode (DM), where CM enables comp, and the UE would be assigned to CM if and only if it necessarily needs multiple point transmission, like this. Otherwise, UE in DM would only receive packet from a single DU, like this. CU and DU is connected via wire fronthaul, and here we only consider downlink transmission. The SINR of UEK with service S served by DUN can be expressed as this, where C is joint transmission cluster, P and sigma square are transmit power and noise power, and G is the channel gain, where D is the distance and alpha is path loss exponent. For any DUJ, it's counted as joint transmission cluster if its signal be detected large enough to affect desired signal from DUN. Hence, any DU satisfy this criterion should be transformed into the cluster, specified with power level difference, PLD threshold, gamma. Although CM can achieve higher SINR, it can also lead to higher DOP due to traffic congestion. Selecting FSM for each UE can be regarded as solving resource allocation problem to achieve a trade-off between SINR gain and DLP performance. System delay of a packet for the UE with service S delivered in mode M via DUN is made of sojourn time in CU, transmission time in fronthaul, and sojourn time in DU, where Y is a tuple of mode M and service S. Here are some lemmas provided to integrate processor sharing model into flexible functional split networks. Lemma A. Sojourn time of an arriving packet at IFXU to the UE with service S in mode M can be written as this, where X is C and D, meaning CU or DU. W is the process load of service S and the server of XU, and C is the process load of a packet of services to go through all sublayers in CU and DU. Beta is the process ratio to measure the number of sublayers at XU. Q is the number of packets in the server. S is the process rate of a server. Lemma B. The probability that T is larger than tau can be approximated as this equation, where low is the workload, equivalent to the ratio of time processing packets, which is expressed as this. It's related to the number of UE, arrival rate, workload, and FSM allocation ratio, which is denoted as P. Lemma C. The probability that T equal to tau can be approximated at this equation. From the lemma above, the following theorem can be proposed. Theorem 1. Denote system delay requirement of services as T required. The DLP of a packet transmitted to a UE with services via env DU in the FSMM can be written as this equation, where the uppercase Z is the maximum tolerable packet number of XU in FSMM when the packet of a service S arrives. Note that all proof of theorems are omitted here, but can be referred to the paper. Theorem 2. In a considered flexible functional split network, the maximum tolerable packet number of XU, Z, can be expressed as this, where this notation denotes floor, and uppercase T is the maximum tolerable delay in the server of XU in FSMM when packet of service S arrives, which is denoted as this. According to reference 10, mean received signal power of a UE from DUs with distance RL to RU in two-dimensional PVP environment is this, where RL and RU are the nearest and farthest distance. The mean SINR of a given UE with service S can be written as this, where uppercase gamma is the SINR of a UE with service S when its nearest DU is located at distance R, and B is the special case of joint probability, this one, where first to nth nearest DU is located at distance R1 to Rn, which is expressed as this. Uppercase A by R is the upper bound of the distance that Cm will be activated according to PLD strategy. P bar is mean received power from DUs within this range. The optimization problem involves minimizing the DLP of UEs with URLC service while guaranteeing the mean required SINR of all UEs, which can be expressed as this. Metric set bold P includes design variables representing FSM allocation ratio, and T denotes the system delay. Theorem 3. Solving the optimization variable P in 18 is equivalent to determining FSM for each UE. There are two steps in optimal FSM decision algorithm, OFD. The first is feasible set reduction, FSR. Theorem 4. The mean SINR in equation 16 of a service S is proportional to the value of PLD threshold, gamma. Thus, mean SINR constraint in 18 can be satisfied after finding a lower bound of PLD threshold, gamma L of service S. Lower bound of FSM allocation ratio PL for service S is then determined using 19 based on the obtained gamma L. FSR can be expressed as this. Second, globally optimized solution search, GOSS. After FSR method, the considered problem in 18 can be rewritten as this. Then the theorem 5 can be used. The objective function in 20, this one, is a convex function with respect to both P. There the Newton's method can be used and a globally optimized solution can be obtained. Then computational complexity of the proposed algorithm is denoted as this one, where En represents number of servers and the considered networks. So the step GOSS can be expressed as this one, where H is the Hessian matrix and this one is the first derivative of DOP function. After aforementioned analysis, problem transformation, and algorithm, here comes performance evaluation part. The UEs of ENBB and URLC service as well as DUs are distributed with PPP property, and some relevant key parameters are summarized in this table. Some FSM decision strategies are here for performance comparison. One is LCM method, which uses CM to serve OUEs, and the other one is random method, which chooses FSM for each UE by randomly assigning the value of P after implementing the proposed FSR method to guarantee the SINR requirements. This figure shows the convergence of proposed OFD algorithm with different density values of ENBB UEs, lambda E. And it can be seen that OFD algorithm is convergent within 5 iterations, and the DOP becomes higher as lambda E increases, which is caused by the congestion of the servers. And this figure shows the optimality of proposed OFD method, where multiple methods are compared, and OFD achieves lowest DOP due to its ability to search for a globally optimized solution. The DOP becomes higher when the number of ENBB UEs increases, which is caused by the traffic congestion in the server. This figure shows the percentage of UE number with different PLD threshold. As it can be seen, with the increment of the PLD threshold, it will result in a higher probability of activating CM for UEs and vice versa, based on the PLD threshold criterion. This figure suggests that the FSM for each UE can be determined for a given PLD threshold and validates the discussion presented in Theorem 3. Finally, here are the conclusions. We proposed OFD algorithm for obtaining optimal functional schema selection for serving mixed ENBB URLC services for 5G and R. With processing, sharing model, and comp, it can achieve low latency URLC transmissions sustained by required SINR of ENBB traffic. FSR is used to reduce the feasible set of candidate solutions firstly, then GOSS is designed to minimize DOP for URLC constrained by SINR requirement of ENBB. Convergence and optimality have been demonstrated by simulation results, and the performance shows that it strikes a trade-off between URLC and ENBB services in terms of different PLD and densities. Thank you for your listening and participation.